Hi Year 12. Today's video is looking at motion and vectors, and we're nearly at the end of our vector journey for now. So let's have a look if we can have a look at some of these. Okay, I've talked about this briefly in class before, and it's the idea of being able to split a vector up into components which are horizontal and vertical. So if you have a look at our vector diagram down here that we've got, our vector here, vector u, is r units in size, or has a magnitude of r. But when we think about how we could make that vector up as the sum of our vector triangle additions, we would have a component that moves along here and a component that moves up here. So we'd actually have a horizontal and a vertical component. So the horizontal would be our x value and our vertical value would be our y value. And our angle that our vector makes with the x-axis is theta. Remembering that when we're working on angles, we're starting at the x-axis and we're going anti-clockwise around as if we were looking at the unit circle. So if we use this triangle here, and note that it is a right-angled triangle, and we worked out what sine of theta and cos of theta are, what we're going to get are these two little parts down here that I've written here. Okay, so we've got a hypotenuse of r, a vertical amount of b, and a horizontal amount of a. So sine of theta is opposite on hypotenuse. So there's our value there. If I multiply by r, I get that r sine theta is equal to b. Similarly, we can do the same for cos. Cos is adjacent on hypotenuse, so cos of theta is a divided by r, which we can see over here. Multiplying by r, I get r cos theta is equal to a. So what we end up with is this component that relates to b and one that relates to a. So if we think what we would be doing when we would be writing our name for our vector u, as a position vector, our vector u, which starts from 0 and going to point up here, which would be, we could call that point P or whatever point that is, it's made up of its x component and its y component. So I've written up over here that our vector u could be written as a column vector in terms of a and b as a and b. But similarly, if we popped in there our a and our b values, we could write our vector u as r cos theta, r sine theta. And that's something that's really important to remember. You should have looked at this in terms of the unit circle already, earlier on in year 10 or earlier in year 11. But you can always, if you forget, go back and have a look at how that's derived. Okay, let's go and have a look at our first example here. Let's move that over there a little bit. And what it says is a body experiences an acceleration of minus 10 meters per second. Now, if you have not done this in your advanced course yet, or you haven't seen physics, acceleration is velocity per time period, and velocity is meters per second. So we end up with two lots of seconds. So acceleration is meters per second, which we often write as meters per second to the power of minus 2, but it's basically telling us it's meters per second. Oops, hang on. Meters per second is what's happening, hence the minus 2. So that's generally how we write it in physics, and that's generally the way that I will write it here for us. So we're saying a body experiences that acceleration. So we've got a magnitude here of minus 10 and a direction of 135 degrees. And we need to find the vector for the acceleration of this body. So I've drawn a diagram over here. Here's our x and y axes. Remember, when we're measuring angles, we're starting from the x-axis in our positive direction and going anti-clockwise. So I would have 135 degrees here, and here's my vector. We just want a name for that vector. Now we know from above that we can write our vectors as r cos theta, r sine theta, and that is what I have done. So our r, remember the minus has to stay there. The minus is important, so it's minus 10 cos 135 minus 10 sine 135. Now, you are in extension maths, so we don't use decimals, okay? So you should be looking at that minus, that 135, and going, okay, what can I do with that? So second quadrant, we want to go 180, take away our 135, and that will give us that equivalent angle in there that we can deal with. So let's do that using your special triangles, which you've got on your HSC formula sheet. There they are over there to the side. Okay, so that will give me And thinking also, sorry, of all stations to central, we're in that second quadrant. Sine is positive, cos is negative. So for my first part here, minus 10, cos is 135. I get minus 10 times a negative value. Okay, so it's going to be minus 10 times minus cos 45. And negatives go away. Over here, the sine is still positive, so I end up with minus 10 sine 45. Popping those into your triangles, you're going to get 1 over root 2 for each of those. So what I'll end up with is 10 over root 2 and minus 10 over root 2. We could leave it like that, but hey, let's rationalize it and get rid of the root 2 on the bottom. So multiply both by root 2 over root 2, and that will simplify it. So it looks a little bit nicer. The root 2 and the root 2 become 2, so 10 on 2 becomes 5, and the root 2 stays on the top. Same as the bottom, but we just have a negative there. That's our vector. 5 over root 2 minus 5 root 2. So if we go back to our diagram, does that make sense? Is our x value a positive? Is our y value a negative? Are we okay? So going back to our diagram, it doesn't actually look nice. It doesn't actually help us, but what we actually didn't really, I guess, think about was our vector probably is going the other direction in that it was a negative. And so the position vector of this, although that's correct, would probably sit down here, in which case we would have the values that we were after. But we've got the right answer, and that's okay, because remember when we're working in our vectors, they're actually giving us those position vectors, so that's fine. Okay, let's look at the next one. The next example. So we have got two displacement vectors. Okay. Vector u and vector v, 3i minus 4j minus 2i minus j. I'm not going to draw it right now. It says find the magnitude and direction of the resultant vector. So let's just draw the resultant vector. Thinking back to earlier on, how do we get u plus v? We just sum our components. So vector u plus vector v, let's sum our x components. We've got 3i minus 2i, and we've got minus 4j minus j, which ends up with, what have we got? 3 minus 2, which is 1i, which is just I, and minus 4, so there's a minus missing in there, minus another j is minus 5j. That's our resultant vector. Let's call that w. Call that guy w. Let's go and draw that vector so we know what we're dealing with. So we'll pop our x and y axes up here. Okay, so remembering if you prefer to write this as a column vector, we'd write that as 1 minus 5. So we'd have the value of 1 up here. We'd be at minus 5 down there. So it's a little point down here. Okay, there is our resultant vector. So what it's asking us to find is the magnitude and the direction. So the magnitude, we've done that lots already. Okay, is the sum of the components, which is 1 squared plus 5 squared, or minus 5 squared. We know that's the same as 5 squared, which is going to be 1 plus 25, which is root 26. We're going to leave it as root 26. Can we simplify that third? I don't think we can. We're going to leave it like that. Okay, so that's how long that line is, but we need a direction. So remember, our direction is measured all the way in that direction. So that's the angle that we want to find. But to make it easier, let's find this little angle theta in here first. Theta in there. Oops. Here's a right angle triangle. How are we going to do that? Okay, we know that we're 1 across and we know that we're 5 down. So, theta. What do we want? Sine, cos, or tan? We don't have the hypotenuse, so we want tan of theta is going to be equal to opposite on adjacent. So tan of theta is 5. So theta is inverse tan of 5. Let's pop that in the calculator. So theta is 78.69 degrees, but we want the whole angle. So we want to take 360 and we want to take away 78.69 degrees and see what that equals. It's about 281. So it's 281.3 degrees. Have we answered our question? The resultant vector is, and we might write a little solution in there. So the resultant vector u plus vector v is root 26 in magnitude with a bearing of 281.3 degrees. Remember, a vector has both magnitude and direction, and that's what we've shown there. Let's look at the next. Now, we need to be really careful with this next question because I just did it and then I actually misread it. So let's have a think. So it's not actually talking about vectors to start with. It's talking about a bearing of, and this is a true bearing. So let's have a look. It says a plane's controls are set for 250 kilometers per hour. So I've drawn that on a bearing of 040 degrees. So that's true. So when we were talking about bearings, we were talking about taking things previously from north, okay, and around 40 degrees. So that's 40 degrees in there, and that's what I did wrong before. I was looking at the bearing of the vector and going up that way, but it's not actually what that said. There's also a westerly wind of 55 kilometers an hour. Now, we could pop that westerly wind down there, or what we could do is we could pop that westerly wind up here. Now, this is not to scale by any means. Now, I'm going to pop it up there because remember, we can pick up a vector and move it, and it's a lot nicer to have the vectors tip to tail in that first quadrant. And it's coming from the west, so that's still coming from the west. It's just sitting at the top. You want to find the actual speed of the bearing of the plane taking the wind into account. So we basically want this sum of those two vectors. So I want that addition in there. Okay, so if we call that one u, we call that one v, we want u plus v. Okay, so I might try and do this diagram a little bit neater for us on the board in class. But what we're basically doing, let me try and change our pen color there for a second, hold on, is we're now thinking about vectors. Okay, so although my original line here had a bearing of 40, we know that this whole thing's 90. So I've got 50 degrees up there for my first vector. And that's what I need to think about. And this second vector here, my westerly wind vector, has a 0 degree bearing. Okay. Or a 0 degree angle as a vector because it sits on the x-axis. So I guess that one's quite tricky in the sense that we've gone from just old trigonometry bearings and we're still using the word bearing, but we're looking in terms of a vector. When we write the vector, we're measuring the vector from the x-axis. So let's figure out vector u to start with. So what is vector u? Vector u is the 250 kilometers, which is on a true bearing of 40 degrees, but as a vector, it sits 50 degrees up. So in that case, remember that was r cos theta. So 250 cos 50 degrees, 250 sine 50 degrees. Now, I can't do anything with exact value triangles for the 50 degrees, so I'm going to leave it like that for now. And vector v, well, vector v is interesting, isn't it? So it's got an x component of 55, but it doesn't have a y component, but let's put it in as if it was. Let's go 55 cos of 0, 55 sine of 0, which is equal to, what have we got? Well, cos of 0 is equal to what? It's equal to 1. So we'll get 55 times 1. Oops. So we'll end up with 55 as our x component. Sine of 0 is going to be 0. So we're going to zero out on the y component, and that makes sense because we've only got the x component because it was a westerly wind. So to get our resultant vector, which is going to find the actual speed and the wind taken into account, we want u plus v. Okay, so we're going to have to add our x components. So our x components and our y components separately. So our x component is 250 cos 50 plus 55. And our y component is 250 sine of 50. Okay, so here we're jumping between vectors and trig again. So there's our vector in vector format. So that value there would result at that point up here. But what it's actually getting us to find is the actual speed. Now, speed is a magnitude. Okay, so we need to find the magnitude of that vector, which we can do, and the bearing. So I probably used the word bearing incorrectly in the last question, but bearing is the angle that we can look at is in terms of true bearing. So what we want to do is we want to find this angle in here. Okay, that would be the angle of the vector, but as a bearing, we'd take it from north and we'd find that 90 minus our theta. So that's what we want to do. So let's see if we can do that. Finding the magnitude. Okay, so the magnitude of vector u plus vector v is the square root of, what have we got? 250 squared. Well, let's just pop it all under a square. Square of the x components plus the square of the y components. Okay, so I've just got the x, got the y, and squared. Zoom down a little bit there, which is actually 288 kilometers per hour. So in that case, you're going to need to pop that into your calculator. Now I've run out of space here. I'm not using my space really well here at the moment. Now to get this angle theta, okay, we're thinking of a triangle here. That is a right angle. We're going to be in terms of tan because we don't have, well, we could, yeah, we don't really need to use, no, let's just go tan. We're going to go opposite on adjacent. Okay, so that's our vertical component divided by our horizontal component, which is 50, make sure we're using the right vector, which is 250 sine 50 divided by 250 cos of 50 plus 55. Let's pop in our calculator and get theta. I'm just going to go to the nearest degree. So the nearest degree is 42 degrees. We're nearly there. Let's go back and double check what we were doing. Sorry, I'll just zoom out of there. So that gave us theta in our diagram. Okay, but remember we wanted our bearing. So we need to have 90 minus 42, which is, what's that, 48. So we've got theta, or our bearing, is 48 degrees. So our solution is going to be that the resultant vector is 288 kilometers an hour on a bearing of 48 degrees, or 48 degrees, or you might write it as 48048 true. Okay, let's do the next one. Okay, so this takes a little bit of thinking. So we want to find the resultant force of these two vectors. So we've got a vector that's called vector u, and it's 100 newtons, and it makes an angle of 52 degrees with the negative x-axis, and vector v, which is 85 newtons, which is making an angle of 32 degrees below that x-axis. But remembering what it actually means when we're finding our vectors, we want to look at the angle that starts at the positive x-axis and moves around. Okay, and that's the first thing I've got to look at here. So this vector u here, okay, it has a magnitude of 100, but our r, in terms of in finding our vector cos and sine components, is going to be 100. And the angle it makes with the x-axis, the positive x-axis, is 180 minus the 52 degrees. So it's actually 128 degrees around there. And we can also find out that angle in there, which just happens to be 38. So we can say that that vector u there is 100 cos 128, 100 sine 28. That's the name of that vector, and that relates to that point up there. The second vector down here, we can do the same. We know that the angle, 32 degrees, yeah, that's the angle that it makes with this axis, but we want to start at the positive x-axis and move around. So that is 180 plus 32. So we get 212 degrees as the angle. The size of that vector is 85. So our r is 85. So it's 85 cos 212, 85 sine 212. Okay, so we want to find the resultant vector. Now, if we were drawing that resultant vector, and I'm going to redraw it again, okay, I'm going to basically look at the parallelogram method, pick up this little vector here, and I'm going to plonk him at the top up here because I like mine from tip to tail, and that's my 85 Newton vector. And I also know a lot of things about it. If you wanted to, you could go and redraw your angles there. So you would know that that vector had a 32 degrees in here. we could work out our angle in here. Got lots of geometry to work out little bits of information about it. But my resultant vector that I want to find is this one up here. That's my u plus my v, okay? And we want to find the angle in here that meets up to that vector. Okay, so u plus v is going to be straight off u plus v. We've got our u, we've got our v. So if we just add our x components and our y components without even thinking of our diagram, I've added my x's, I've added my y's. To find the magnitude of that vector, because that's what it wanted us to find, the resultants of these two forces. Okay, so let's just find the size of it and its direction. What we're wanting to do is find the magnitude, so it's the x component squared plus the y component squared. It's going to be a little bit fiddly on the calculator, okay, with that one. And we're going to end up with 137.8 newtons. Now, we know that those are our components, okay, for our u and v vector. So to find our angle theta, okay, and that's the angle that I'm going to find in there. Okay, I'm popping that in my calculator and end up with 166 degrees. So I've got a bearing of 166 degrees and I have 137.8 degrees, 8 newtons.